Okay, so hi everyone. This is Takashi, and I am a lecturer at the University of Tokyo and visiting scientist at Regan AIP. We have been hosting TrustML Young Scientist seminars, or TrustML YSS, which is a seminar series that features young scientists giving talks and discoveries in relation with trustworthy machine learning, led by Jingfeng. Today is the 64th seminar, and I am excited to have Xuanli He. Xuanli is a research fellow at University College London. He received his PhD from Monash University in Australia. And his recent research lies in an intersection between deep learning and NLP, with an emphasis on robustness and security in NLP models, including privacy leakage and protection, backdoor attack and defense, and imitation attack and defense. He has published more than 20 papers in top-tier machine learning and NLP conferences, such as NeurIPS, AAAI, ACL, and so on. Today, Xuanli will give us a talk about imitation attacks and defenses. So Xuanli, we are very excited to learn about your research. And if you're ready, please begin.
Okay, great. Thanks, Takashi, for the introduction, and it's my honor to be invited here to give a talk about our recent work on imitation attacks and defense. Before I move to the major content of this talk, let me briefly introduce myself. So currently, I'm a research fellow from University College London. Before I moved to London, I obtained my doctoral degree from Monash University. Now, my primary research interest focuses on security and the robustness in natural language processing models. If you are interested in this direction, feel free to reach out to me. So in this talk, I will first provide an overview of what imitation attacks are, before presenting some of our work that showcase the severity of imitation attack. Finally, I will transit to the topic of defensive strategies for mitigating the risk associated with these attacks. As we know, due to the recent advancements in natural language processing, tech companies have developed various NLP models and deploy them as APIs on their cloud platform. End users can use these APIs for their own businesses. Although the end user's experience is quite straightforward, the development of these APIs is much more complicated than we thought, and it incurs the significant cost. First of all, as the dominant approach in artificial intelligence, deep learning requires large amounts of the data for the training purpose. Acquiring and annotating data are super expensive. Secondly, this model should be developed and trained before they can be used to address the specific needs of the end users. Lastly, as with any API, the costs of model deployment and maintenance are substantial. Therefore, to promote the healthy market growth, API owners adopt a pay-as-you-use policy. But what if I don't want to pay the service charge? Well, there is a solution. That is, we can steal the cloud service via the imitation attacks. Basically, imitation attack, also known as model stealing, it's aimed to imitate the functionality of the victim model, that is the remote API. This process involves 3 steps. Firstly, attackers can build a set of the queries and transit to the victim model for annotation. Subsequently, attackers can use the resulting prediction to obtain a surrogate model. Note that depends on the task. The prediction can be varied. For example, for the classification task, the prediction is a probability, or they predict the label. For the text generation task, the prediction is a sequence of a token. Finally, as the victim model has been locally replicated, attackers are not required to pay the service charge. But how can we conduct imitation attacks in practice? Let's assume that we can use the following objective to train the victim model. So that is, we can minimize the loss between the model's prediction and ground truth. Regarding the training of the imitation model, we can minimize the loss between the victim model's prediction and also the imitation model's prediction. If you look at this objective, right? So this might remind you of the logic distillation. So principally, imitation attack is similar to logic distillation. However, as we don't have the ground truth label for the inputs, so that's the difference between the imitation attack and the logic distillation. Albeit its simplicity, the performance of imitation attacks is remarkable. As we can see from this table, imitation attack are capable of imitate the victim model in various classification tasks and achieve the comparable performance. In addition, researchers from UC Berkeley have discovered that one can use the imitation attack to imitate the commercial APIs such as Google Translate and also achieve the comparable performance. To date, the literature on imitation attack still focus on achieving the performance comparable to the victim model. As the imitation model are still inferior to the victim model, the owner of the latter are not needed to be too concerned about the threats from the imitation attack. But can imitation models support the victim model? Our answer is yes. As we know, imitation attack can imitate any API. Thus, we can imitate multiple APIs and obtain a response from each of them. By using ensemble learning, we can combine this response together and train an imitation model that supports all the API services. This can lead to a significant loss of the market share for the commercial APIs, and making their product less attractive to the end users. In addition, prior work assumed that training dataset for victim model and the queries used for imitation attack were identical or draw from the same distribution. However, it's evident that the domain of the training data used by victim model is usually unknown, because victim model is a black box for us. Besides, attackers tend to express an interest in particular domain. Therefore, there exists a domain mismatch between them. As we know, models' performance suffers in the cross-domain settings, but it's unknown how this can affect the cross-domain imitation attacks. To demonstrate the performance of the cross-domain imitation attack, we employed movie settlement analysis and financial settlement analysis as our queries for our analysis. We first examined the performance of two commercial APIs. As we can see from this figure, it's evident that these two APIs were not trained on the financial domain, resulting in a significant performance degradation in comparison to the movie settlement analysis. However, after the imitation attack, albeit the weak performance of the victim model, an imitation model can minimize the domain shift and obtain a superior performance compared to the victim model, especially on the financial settlement analysis. We can see a significant boost. In addition, by conducting ensemble imitation attack, we can see additional boost. Thus, with the aid of the cross-domain and the ensemble imitation attack, we are able to obtain a superior performance, the superior and cost-efficient imitation model. This can pose a significant threat to the commercial APIs and challenging their market share. Now we understand that imitation attack aims to obtain a surrogate model that performs similarly to the victim model. As the victim model is a black box to attackers, attackers may leverage the imitation model to gain the insights into the working of the victim model. I believe most of us are familiar or probably hear about the adversary attack. So adversary attack is a type of attack which can manipulate the input data to fool the victim model. This is a very famous examples from the Ian Goodfellow. Black box adversary attacks are type of the adversary attacks where the attacker doesn't have the access to the internal working or parameter of the target machine learning model. In other words, the attacker can only observe the inputs and the outputs of the model. Below is an example show how can we conduct the black box adversary attack on sentimental analysis attack to identify the significant tokens that underpin the model's prediction. Attackers can systematically remove each words from the inputs and submit the altered text to the model. After pinpointing the critical tokens as shown in this figure, attackers can manipulate the inputs to deceive the victim model, leading to the false prediction here. It's evident that there are several drawbacks of black box adversary attack. Firstly, black box attack often require a large amount of the queries to the model in order to generate the adversary examples. This can be computationally expensive and cost-consuming. Secondly, black box attack typically involved repeatedly querying the model with the similar inputs. As you can see here, right? So we need to repeatedly repeat the input, the tokens to construct the queries. So this can be perceived as a suspicious behavior and resulting being banned. Finally, the quality, the adversary examples generated by black box attack is really not as good as the one generated using the white box attack. So this can limit the effectiveness of the black box attack. As we know, compared to the white box attack, to the black box adversary attack, white box adversary attack is much more efficient and effective. Therefore, attackers can use the imitation model to generate a plethora of the adversary examples. As we know, the imitation model is actually a replica of the victim model. This adversary example may fool the victim model as well. This process allows attackers to gain a better understanding of the victim model's weaknesses and vulnerability here. It's worth noting that the queries used in the imitation attack are varied, which makes it less probable to be detected and banned in comparison to the black box adversarial example. To demonstrate the effectiveness of using the surrogate model for transferring the adversarial examples, we consider 3 black box attacks and 1 white box attack. Note that all adversarial examples are generated using the surrogate model, and their impact on the robustness of the victim model is evaluated. To assess the transferability, we compute the percentage of adversarial example that's resulting flipping prediction on the victim models with higher percentage, indicating a better transferability. This figure demonstrates that white box attack has a significantly better transferability, nearly twice as much as the black box attack. This demonstrates the danger of the imitation attack, which can lead to subsequent attacks that are more severe than previously anticipated. Besides, co-current work indicates that one can use the imitation model to craft adversarial examples and transfer to the commercial systems such as Google Translation. So this finding indicates that our work is not a laboratory hypothesis. It can be applied to the real-life scenario. As we know, deep learning models are incredible learners. It has achieved a remarkable performance on multiple NLP models, such as segmental analysis and translation, and also the grammar check. However, these strengths can become weaknesses. Previous work finds that in addition to the primary task, these models can accidentally overlearn the task irrelevant but private information such as gender, location, and age. This can lead to a privacy leakage. In the light of the fact that imitation model can mimic the behavior of the victim model, the possibility arises as to whether the confidential information can be translated from the victim model to the imitation models during the imitation attack. Thus, the imitation model also has a potential to compromise the privacy. To verify this hypothesis, we suggest investigating the privacy leakage in the context of imitation attack, similar to the conventional study in the privacy leakage. After the imitation model is obtained, we can convert the inputs into the hidden representation. After that, an inference model can be employed over this hidden representation to deduce the confidential information from the inputs. We refer this type of the attack as attribute inference attack. In addition to our approach, we consider 2 baselines. The first one is majority class. So that is, we use the majority class as a predictor label, also known as random guess. In the second approach, instead of using the imitation model, we use the vanilla pre-trained BERT to encode the inputs and project into the hidden representation. And those, as we can see from this figure, in construct to the baseline models, imitation model exists significant privacy leakage. Please note that, so here in this figure, higher number indicates that less privacy leakage. And therefore, in addition to the primary functionality, imitation model is susceptible to the attribute inference attack. Multiple threats has been identified from imitation attack. This highlights the need for protective measure to protect the IP of the victim model. In this talk, I will discuss the protection measure for both classification task and text generation task. Let's first look at how can we protect the classification tasks. Given that the responses of classification task consists of the predicted probability for each label, we can modify them to fulfill the defensive objectives. First of all, we propose to use a temperature over the softmax layer to scale the probability vector as shown in this formula. Notice that when the temperature is approaching to 0, now we only return the predicted labels as others are zeroed out. Besides, we can perturb the prediction using the Gaussian noising. That is, we sample a noising from the Gaussian distribution with the zero mean and sigma variance and add it to the predicted probability. And after that, we do the normalization to guarantee that so the vectors is sum up to 1. Thirdly, Mark et al. Propose using an adversarial loss to discourage the knowledge decision from the victim model to the imitation model. In their strategy, they first train a nasty teacher like what we train the victim model. Then they train the victim model. In addition to the primary objective, they include the adversarial loss. By using this loss, they hope that they can discourage the knowledge distinction from the victim model to imitation model, such that they can prevent the imitation attack. Finally, we propose a novel method called most list. In this method, we set the predicted probability of the most and the least likely categories to 0.5 plus epsilon and 0.5 minus epsilon, and zero out all the zero out others. Primarily with the exception of the significant perturbation. So here, if we set the variance too high, this will cause the significant perturbation. And except this one, none of this method can impact the most probable prediction, thereby preserving the performance of the victim model. Regarding the defensive capabilities, our approach is more efficacious in mitigating the imitation attack than any other defensive strategies, and almost make the imitation attack useless. Now we can move to the protection of the text generation tasks. As we know, the responses of text generation tasks returned by API are sequenced tokens, which preclude the use of the safeguarding method developed for classification tasks. So how can we protect the text generation tasks? Well, there is a solution. They use the backdoor for the defense and the verification. As we can see from this figure, the APIs can randomly select the small fraction of their requests from the users and answer them with the incorrect result as a backdoor. Here I highlight the incorrect result here. Meanwhile, API owners should store these queries and answers for post-hoc verification. Once API owners suspect that there is an IP infringement, they can send the stored queries to the suspicious model. If the model returns the backdoor answers, then it's likely to be an imitation model. However, there are several drawbacks of using backdoor method. First, as we notice that, so the backdoor will return the incorrect answers. Thus, users tend to be dissatisfied with the incorrect response and may switch to the alternative services offered by the competing companies. Secondly, API owners are required to store the query answer pairs for the all high traffic users, leading to the significant storage consumption. Thirdly, the verification process can be computationally expensive as all backdoor queries need to be thoroughly examined. Finally, if the suspicious model requires payment for each query, then the verification process can become expensive. In the literature of the cyber security community, experts have developed some tactic called Watermark to protect the IP of machine learning models. This process involved generate unique and identifiable watermark and embedding this watermark into the protected model by modifying the weights or the activation. If the owner of these models suspect there is an IP infringement, they can analyze the model's prediction and track the instance where the watermark is present. By using this watermarking method, we can prevent the unauthorized use and guaranteeing that the models are only used for the intended purpose. Inspired by this, we propose to use watermark to protect the IP of the victim model. The following are key principles to consider when implement the watermark method for imitation attack. We should return the semantics of the original output. The watermarks should be transferable to imitation model and verifiable by API owners only. Finally, and optionally, the watermarks should be explainable to human judge. That is for the lawsuit. Basically, text generation model aims to know a mapping from the input to output. As we know, imitation model can mimic the behavior of the victim model. Thus, if we can inject the watermarks into the output, these watermarks might be embedded into the imitation model as well. Following the key principle, we propose using the synonym to achieve the watermarking objective. Here is the workflow for synonym replacement. Firstly, it's necessary to select the target words from the training data. Then a list of the synonyms for each word can be obtained using the wordnet. Finally, based on the watermarking rules, we can replace the target words with the synonym. Concretely, our watermarking approach aims to modify the original distribution and resulting the watermark distribution that serves to protect the IP of the victim model. However, this symbolic approach is susceptible to be reverse engineered. As shown in this figure, the watermarked words can be discerned by scrutinize the distribution of watermarked corpus and any online corpus. This is because compared to the common words, the distribution change of the watermark words as highlighted here are much more significant. So which means that we can reverse engineer the watermark words. In the light of the limitation of this basic substitution method, we propose an objective that can preserve the overall distribution when selecting the appropriate synonyms. However, if we take a close look at the target words and the synonyms, they subject to multiple conditions as shown here, each with its own conditional distribution. Our approach aims to modify this conditional distribution in accordance with the selected synonyms. So we can change the conditional distribution, and like this can achieve the watermarking purpose here. Regarding the objective, it can be formulated into two components. Firstly, an indistinguished objective. So that is here, aim to minimize the difference between the pre and post watermarking word distribution as shown here. The objective can guarantee that the overall distribution is not changed. Secondly, a distinct objective can guarantee that the conditional word distribution can differ significantly from the original one to function as a verification mechanism for detecting IP infringements. So that is a visual understanding for this one. When it's come to the conditions, we consider two linguistic conditions. The first one is the part-of-speech tag of the target words for the labeling words. For example, we can replace the region with area if and only if it's the part of the speech tag of the previous words is prolonged, not for the determiner. Similarly, we can do the replacement if the incoming ACK of the dependency is subject, but not for the object here. Now, let's have a look on the performance of our approach on translation tasks. Primarily, our approach results in insignificant performance deterioration compared to the baseline without any watermarking protection. This issue that our approach doesn't cause the incorrect response to the users. Simultaneously, our approach facilitates the attribution of the IP of the victim model by enhancing the identifiability for the imitation model. This issue that by using our approach, we can identify the violation of the infringement during the imitation attack. Similarly, we observe the similar behavior for summarization task. Both generation quality and identifiability are guaranteed here. As mentioned earlier, a simple replacement is less surreptitious, as these watermarks can be discerned by using the distributional analysis. However, the watermarks generated by Capture, that is the conditional watermarking process, it can be obscured with the commonplace words as shown in this figure, render them less conspicuous. As we know, the recent breakthrough in large language model has caused the paradigm shift in the interaction between machine and human. For example, I use ChatGPT to help me to prepare the slides for this talk. However, the misuse of this large language model can cause the social and ethical issues. So to address this misuse, pioneer work proposed to use the watermarking as a means of the synthetic detection. But can we do something else? So this is the open question for all of us. For me, I don't have a clean answer. If you are interested in this direction, free to reach out to me, and we can work on this direction and come up with novel ideas to alleviate these concerns. To sum up, cross-domain and ensemble imitation attacks can exacerbate the risk of imitation attacks. One can use imitation model to study the victim's vulnerability and weaknesses. Finally, it's possible to effectively protect the IP of the victim model. Okay, so it's advertising time. I and my collaborator will organize a workshop at EMLP 2023. So for this year, and it will cover imitation attack, defense, privacy leakage, and protection. Also the backdoor attacks and the defense. I hope we can see you in Singapore. Appreciate the support from my collaborator Chongkai and Lingjun. Okay, so that's all. And thanks for your attention.